We're really happy to have you here with us today to hear and see the last presentation in this webinar series. So to get right into it today, my name's Tim Hunter. I'm going to be presenting, and the last topic today is load-driven design, revolutionizing product development with simulation and test. So our technical team here at Wolfstar Technologies is me. I'm Tim Hunter. I'm the president and founder of the company. I've got a PhD in engineering. I've got 35 plus years of simulation design and test. Spent bulk of my career at Harley-Davidson, and I'm the founder of the company and the developer of the software that we'll be seeing today. And then Cindy Murphy is our director of engineering, and she's got 30 plus years of experience, master's in engineering, and she spent a lot of time at Harley-Davidson too. So she's part of our engineering team here at Wolfstar, and we're here to support you in any of your product development needs. And I'll be doing the presentation today, so let's just get right into it. Okay. So if you've caught our previous webinars, we've seen this V diagram a lot, and this is great. You know, this is really trying to take us through the product development process the way we need to go. And on the front end, we start off with the CAD design and simulation tools that we've got, and we can do virtual iteration very quickly and easily with these simulation tools, so we can really explore our designs, and that's great. The only downside is that's based on previous knowledge and assumptions, and that knowledge and assumptions can be wrong. And on the other side of things, though, when we go to prove out our designs, we go into the physical world and we do testing, and the testing is great. But the downside is with the testing is that it is expensive and slow. But the huge upside is that it's based on the real world. And so our challenge here is, how do we take our knowledge from the testing that we're doing in the physical world and bringing it back into our virtual world, so we can use that knowledge, so we can do better simulations and doing better design iteration here. And this is all part of our design, build, test cycle that we've got in product development. And it's a necessary evil, but we want to keep that down to bare minimum. Okay. So, and today, to kind of demonstrate that all, we're going to develop a Razor scooter. Okay, so this is an example we've got on a Razor scooter, and I think even if you guys aren't making Razor scooters, I think what we're showing here and the concepts being presented here, you can apply to any of the products you've got. So this is going to be a kind of a fun exercise to go through to show you what we're doing with product development. And so I just want to give you a fair warning ahead of time. Our previous presentations haven't had any mentions of any of our products. So today we are going to be focusing solely on our products. So our TrueLoad load reconstruction software and our TrueQSE quasi-static event software. We're going to be showing and demonstrating those software here today, but it's a huge part of being able to do this knowledge capture, and you'll see how we use that, and I think you'll be able to see how to apply that to your things. So fair warning, I'm going to be talking about my products throughout this today, but we'll see some really great stuff. So why a Razor scooter, right? You know, well, a Razor scooter, well, it's in the time domain. That's where we spend our lives, in the time domain. So it's something that we want to do. It's dynamic, so there's all sorts of dynamics going on in these things. It's totally nonlinear loading. It's complex. And it's just non-intuitive on how you set up the loading on this thing. And frankly, it's just plain fun. So let's go have some fun and take a look at this Razor scooter and see what we've got here. So if we were to try to use traditional load measurement devices to attack this Razor scooter, we might use a pancake load transducer here to get maybe the XYZ loads at the foot, right? And we use a wheel load transducer to try to get the loads at the wheel. But if we did that, we'd have questionable loads that we'd be measuring at the foot, and frankly, to put this wheel load transducer on, we would destroy the rear wheel. So if we use traditional load measuring techniques, we couldn't really do it because we'd destroy our test article. So this really wouldn't work. So what we're going to do is we're going to do a different direct approach, and we're going to leverage our TrueLoad software to do that. So the way we do this is we take an FEA model, and in the FEA model, we we conceive what loads do we want to do. So on my FEA model here for this Razor scooter, I said, hey, you know what? I want to understand the XYZ loads at the foot. I want to understand the loads on the axle and the tire patch here, and even a drilling moment on the tire patch. So basically, I'm saying these are the loads I want to understand. So I set up unit load cases in my FEA model, and I solve that FEA model, and then I bring it into our true load pretest software. And our true load pretest software says, hey, place strain gauges here. So it comes up and gives you the ideal locations for placing strain gauges on the structure in order to be sensitive to these loads. And now that you've got that, then it's going to store the correlation matrix that basically takes the strain gauge placement and basically makes us a correlation matrix that relates strain response to load. We store that to disk, and then we go measure the strains in real life. So we just go and instrument up our Razor scooter and measure the strains in real life. And now that we've got those strains, we're going to multiply them by that correlation matrix to back calculate the operating loads. Okay. And this is what we do, okay? So we're going to go through this a little bit more detail, but this is basically what the path is, okay? So the theory on how this true load stuff works, it's all based on linear systems and loads, okay? So linear systems are where loads are proportional displacements, displacements are proportional strains, strains are proportional loads. This is a linear system, okay? We fully realize everything in life is nonlinear. Okay, we understand that everything in life is nonlinear, but we're turning your structures into a load transducer. So we're going to target the nominal linear portions of the structure. So we're going to stay away from nonlinear areas like welds, bolted joints, areas of contact. We're going to be in nice nominal areas where the strain response to those nominal areas remain linear and proportional to the exterior loading. The loading can be as nonlinear as anything. The loading could be sinusoidal, ramp loading, impact loading. That's okay. We just need to keep this proportionality between the strain response and the exterior loads. All right. So I can take this little diagram here and turn it into a couple of equations. Okay. So the right-hand side here, well, that's just F equals KX. So that's Hooke's law. So if your structure is obeying Hooke's law on bulk, then the left-hand side of this triangle has got to work for you too, which is strain times the correlation matrix is equal to load. And we're going to calculate loads as being strains from test times the correlation matrix from FEA, okay? And in the industry, this is known as the theory of influence coefficient. So you could look up some papers on this and you see this equation all over the place, okay? But this is what we're doing here. This is how we're going to do things. So back to our Razor scooter here. So here's the FEA model I've got set up. So you can see here, I've got XYZ loads set up at the foot here. I've got loads at the axle and the tire patch and drilling moments here. So I've got all these unit load cases here and the boundary conditions. I'm basically restraining the top and the bottom of the steering tube translationally. And then I've still got a spinning degree of freedom here that's free. And so I'm using inertia relief to take care of that spinning degree of freedom. Okay, so this is a nicely set up model here. And we solve the FEA model for all these unit load cases. And then we go into the true load pretest software. So here we load it up into the true load pretest software. And the true load pretest software then loads up all of our unit load cases. And then once we've got these unit load cases loaded up, it basically tells us where to place the strain gauges. And then once you've got the strain gauges, then we've got tools to do nice little dimensioning here to show you how to place the gauges on the physical part, okay? So because you need to place the strain gauges in the physical location, in approximately the right location here, okay? So this is all part of coming up with the gauge placement, generating this correlation matrix, and then getting ready to go into test, okay? So now that we've got that, then we just instrument this up. And so this is actually, you were seeing a picture of one of my interns placing the strain gauges on my Razor scooter, and he did a really nice job with all this stuff. So we've got the strain gauges laid out, and we've got get it all instrumented up. And then once we do that, then we just go off and do data acquisition. And we've at Wolfstar Technologies, we use this DTS Slice micro data acquisition system. It's a fantastic data acquisition system. It can collect up to 500,000 samples per second, and it's about the size, about 2.5 inches square. It's great. And we don't make any money from this. I'm just saying it's a great data acquisition system, and we love it. Okay. So this is our data acquisition system. We've got it wired up on a Razor scooter, and here's the strain data. So we ride this thing down the street, collect a bunch of strain data. Here you see we've got 20 seconds of strain data, and we can see us kind of pushing this thing down the street, and you can see our strains, plus or minus 400 microstrain. And the whole idea is we want to take this strain data now and turn it into load. So we take this strain data, present it to our TrueLoad post-test software, and then we get loads. And so now these are the loads here, okay? And so you see a bunch of curves here. It's kind of hard to read them, but really the blue curve here is the fore-aft forces on the structure from the foot pushing the scooter forward. The red curve here, this is a rear wheel vertical force, and the orange curves, that's the downward force of the foot. So, you kind of got all these things going on. And then, and from those loads now, the TrueLoad software, this is just an automatic process in the TrueLoad software. What happens now that we've calculated these loads, the TrueLoad software will automatically go back into the FEA model and generate simulated strains at our strain gauges. And then it plots up these very nice correlation plots. So this plot on the left here, the green curves are the measured strain data, and the blue curves are the simulated strain data from those loads you just looked at. And then we generate these very nice cross plots where we've got measured strain versus simulated strain, and we've got near one-to-one correlation here, okay? With just one button push, you get this type of strain correlation. And this is pretty complex loading going on here with 7 degrees of freedom of loading, and we can do this all in one button push and get this great type of correlation. And we even generate statistics here. So here our average strain error is 3.4%. Okay, again, we get this with a button push. Pretty cool. And just to drill down a little deeper here, I've got a Bob and Wow plot. So the top set of plots are my best of the best, Bob, and the bottom curves are my worst of the worst strain gauges. So you see my Bob plot there. I've got nearly one-to-one correlation, a nice straight line, one-to-one correlation on the 45-degree line. This is perfect correlation. But even my worst strain gauge on this thing, it's a still pretty darn good correlation, okay? So now we've got these loads calculated. We've got high confidence that they're right because we're getting strain correlation all over on the structure. And then we can now take that then and generate operating deflection shapes, okay? So here's an operating deflection shape of our Razor scooter. And this graphic here, I put a section plot through it so you could see the load vector at the foot there, just so you could, because it's kind of going inside of the structure, so you can kind of see the load vector there. And so here we're just seeing a subset of the time history here for our animation. And for all of you guys watching online here, these are QR code here. So if you scan this QR code, you can get this animation on your phone. So you get a 3D animation on your phone if you want to. And this is actually the URL for that, okay? And so this is great. This is great. We get to see what our Razor scooter was doing, right? We've got very highly accurate strain results on our Razor scooter, and we're able to see what's happening on the Razor scooter. So this is fantastic. But we want to do redesign, right? The whole point of this is that we're in product development. We need to iterate and do redesign. So let's do redesign, okay? So I went into the FEA modeling tool, and I made some redesign here. So I came up with this little pattern of these little triangular shaped holes in here. So I pushed this through the structure here, and basically took out all these little holes in my little footboard for my Razor scooter here. It was a 9% reduction in mass. It might look cool. I don't know what cool is, but there you go. And then we can just then all we need to do in the FEA model is rerun those unit loads on our redesign model, and we can come back into our true QSE software, and we can regenerate the operating deflection shape based off those same loads now. These are the same loads that we saw before, and now we see the stress and strain response for our redesign, okay? I mean, the longest part of this whole thing was me figuring out how to push holes through my FEA model, okay? I was doing the CAD work on this. Once I had that solve the structure really quickly in FEA and bring it back into true QSE, and away you go. So the hardest part for me was doing the CAD work, okay? And then once we went into all this, we can look at the responses here side by side, and I've got a cutesy little thing here. I'm just going to bring another window up here. Let's see if I can get this going. So here we go. We've got the two structures side by side here. Let me do this again. So we got the two structures running side by side. So there's our baseline design, and here's our modification. And yes, we get stress risers here. We get some increased stress here because of my cutesy little pattern. But nominally, that's not a big deal. It's nothing that we'd be too concerned about. Okay, everything basically performing more or less the same. The only concern I would have here on my cutesy design is these points in my triangles here. I've got stress risers going on there, right? So if I were to do it, if I were to finalize this design, I'd probably want to go and put some fillets in on those triangles and to take out those stress risers there. But that's totally doable, okay? I didn't want to futz around with the CAD anymore, okay? But you get the idea. It's very easy to go in and explore anything that you want on the design now that you've got the loads, and you've actually got the actual loads driving this thing. So you're not making guesses. You know how this is supposed to go. So, all right, and so this is kind of doing our whole V diagram product development, right? We've gone through the virtual design, we've gone to testing, and we brought that knowledge back into our design and iteration. So it's very easy now for us to do iterations because we captured that loading from the real world, and we brought it back to our FEA modeling system in a format that the FEA modeling system likes. And now we can do our design build testing, not in the real world, but we can do it all virtually now. So that's the great thing here, okay? We are doing our design build test here virtually, okay? So this is really cool. This is kind of showing us how we go from beginning to end here in this whole process in just really a couple of clicks. And we're leveraging our tools here. So our TrueLoad tool is a tool that we get loads, that we calculate loads from strain measurements. So that's what we do in the first part there. And the True QSE tool allows us to interrogate and generate these operating deflection shapes and really look at anything we want on our structure once we've got those loads. And then what we didn't get into too much today is that if we were doing linear dynamics, we could really leverage this into advanced linear dynamics and take these tools and push them into the linear dynamics domain. And you could get some very, very fantastic results in the linear dynamics domain. So these are the tools that we can get to bring to our problem. So we can go from doing in the whole design build test world, and now with the TrueLoad products, we can go from there into a design, simulate, visualize. And this is where we want to be, right? This is where we want to be doing our product development, in the design, simulate, visualize world, okay? So I hope you see that we've got some nice products that can help you out in your whole product development domain, and we'd be really happy to go in and work with you more on your thing. So with these types of tools, we can go from where we've got our scheduled production, commit to production and launching. And with these types of tools, we can gain the knowledge quicker and faster, and we can move those dates up. And so we in engineering can be heroes of the company and bring and get products to market faster and more reliably than we've ever done before. So thank you, everyone. It's been great. This series has been great. It's been really great to talk about these important concepts that we have to wrestle with every day. And here's our contact information. There's our website here, and so please reach out to us at any point. We'd be happy to talk to you more about our products. I think we've got tools that can really help you out in product development and really save you time and money. I know our customers end up eliminating entire iteration, design build iteration cycles in their product development process. It's just a huge cost savings to them, and we'd love to help you out. So thank you very much, and that's the webinar for today. So we'd be happy to talk to you later. Thank you, and goodbye.